Okay, thank you very much, Tarbot, and thank you everyone for coming. When I was invited, first of all, I should say it's a huge honor to be invited and to be a joint invited speaker. I was not expecting it. And also, when I saw that ITP was co-located, I figured I would talk about something that covers all three conferences. And in fact, this is, so the earliest paper on this that I wrote was came out in ITP in 2013. So this is sort of a follow-up, a very long follow-up to an ITP presentation from, I forget which year it was, which city it was, but somewhere. Anyway, so I'm going to talk about a topic that I used to consider not very interesting in the past, and I always, every 5 years or so, there would be a new proposal for a language-free universal interface, and I would always laugh at those things. But now I get to look in the mirror a little bit. Okay, so okay, universal interactive theorem proving interface. So what could be preventing us from getting there? So I have three obstacles in mind. So the first obstacle, I think this is well understood by this community. There is no universal proof system, no universal language, except maybe mathematics, but no one uses mathematics to do formal reasoning, right? So maybe I can do a quick poll of the room. So how many of you, can you raise your hand if you, let's say, have downloaded and run Rock or Lean ever in your life? So that's what I expected, most of you. Keep your hand raised. If you have used any of the HOL variants, Isabel HOL, Hold for Whole Light, you can lower your hands otherwise. And by the way, since this is TABLEAUX and FroCoS, I have to explain that this comma is conjunction. So keep your hand raised if you've used ACL2 or and Mizar and Agda. Okay. Steve, Tarmo, Larry, great. So I've seen. Okay, so now I'll throw the googly. Okay. Abella. Yeah, see, so no one has used all these systems, right? So I think it is fairly uncontroversial that not many people are proficient in a large number of systems, let's say the major ones excepting Abella and then whatever. And one reason for this is that there are different logics, different proof styles, different tactics, different background solvers. Lots of things are different, okay? And so we can say that it is difficult to do interactivity in an agnostic way, a system agnostic way. Now, this is the case, everybody understands this, but this should be a problem in our community, right? Because if we just change perspectives to systems, so let's look at file systems, for instance. It's the same slide, I've just changed a few words, okay? So we could run the poll again if you've used any of these file systems, and I'm sure we have the same result, but not everyone has used all of them. So we can still say that not many people are proficient in multiple file systems because they have different system calls, different libraries, different naming conventions, whatever. But I hope you would agree with me that there's the last sentence there, that it is difficult to do interactivity in a system agnostic way, in a file system agnostic way. That statement is not quite correct because everyone has used a file browser. You know how to move a file from one window to another window. You do drag and drop, you can select a bunch of files, you can rename with, I don't know, right click or something. So there are sort of universal interaction things that happen despite all these differences. So that's the first obstacle. The second obstacle has to do with human-computer interfaces, so the things you use to interact with the computer. So we all started out using, well, maybe not all of us, but because a few of us have a gray hair, so we might even predate keyboards, but definitely keyboards were one of the first ones, and then we had mice, then we had pointing, finger-based input. Nowadays we have speech, right? Speech input, and maybe in the future, if Meta ever gets its act together, we might have VR, right? And in fact, that's not the end, right? So that's some of the user interfaces. And if you think about it, not every computer has every combination of these. So a traditional computer, like the ones some of you might be using, have a keyboard and mouse, let's say, but they may not have a speech interface or a VR interface or a finger. But If you're using a mobile phone, which is also a computer, then it probably doesn't have a keyboard. It probably doesn't have a mouse. It might have finger input. It might have voice input. And if you ever try to do theorem proving on your phone, you realize it's very difficult because it's difficult to use the software keyboard, right? You can't, many of the common keys that you'd like to press are not present, like Control C, right?
Echo keyboard.
Huh?
Echo keyboard.
Okay, well, maybe you have to tell us what these things are, because I have never successfully used it. Okay, anyway, so different computers have different interface devices, and there is no universality in interfaces either. And the very last obstacle that I'll point out is that even if we're doing interactive theorem proving, there is this very irresistible thing that we want to plug our systems to, which are solvers, like SMT solvers, let's say, or nowadays, I think the real big black box is AI or generative AI, whatever that means. So this is the blackest of black boxes, right? And we all know that a sufficiently general black box is indistinguishable from a bullshit machine, right? But fortunately, we can detect bullshit, but still it generates a lot of it for us, right? So on this point, actually, recently I read this blog post by Mike Dodds at Galois, where he was talking. So he works in protocol verification security, and he was talking about how he would use Claude Code to formalize one of his old papers. But importantly, he didn't want to write a single line of lean. Okay, he wanted to just generate the entire thing using Claude Code, and he succeeded. So you can read the blog post where he explains how he succeeded. It's a very interesting post. This is the conclusion of that blog post. You don't have to read all of it. Just read these two sentences. I hope it's visible to all of you. If not, I'll read it out. So the first sentence is that I think what Claude Code really points to is the bitter lesson, underline, coming for formal methods, just as it did for image recognition, language translation, and program synthesis. Okay, so the bitter lesson, if you don't know what it is the thing that making a smart computer algorithm is not going to lead you to any interesting place, because a stupid algorithm with a lot of computation power will beat you, right? So that's the bitter lesson, and it has definitely killed any interesting image recognition algorithm, and nowadays it is probably going to kill computer linguistics. And program synthesis is next, and then according to this blog post, ITP is after, right? It's right after. And another comment he makes is that the reason ITP has never been widely adopted is that it is simply too cognitively demanding for most humans. Okay, so not a very rousing sentence to read, right? So anyway, so three obstacles I'm pointing out: too many languages, too few interaction modes, and too many black boxes. Okay, so this would probably mean that this is a difficult domain, and am I actually going to solve all of these? Am I going to surmount all of these obstacles? No, the last one I won't. But I have some thoughts about the first two. Okay, so I have this system called Profound. It's based on deep inference, so the name comes from deep inference. And if you have internet access, I would ask all of you to go to this URL, which I will as well. And it's a system that you can run and use yourself. This is what it looks like. Okay.
Can you show the link again?
Yes. Sorry, I could probably write it somewhere. So it's .sh, which is a link shortener, and then Profound. Okay, I'll just lay this on the screen. So this is what it looks like. I think I probably need to make the. Oh wow, that's not a plus. That's something else. What's it? How do I get a plus on this keyboard? This one. Okay. That is it. Okay. All right. Got it. All right. And I'm going to give a very quick demo, which may or may not make sense to all of you. So this is an example that I've pulled out of the Isabel tutorial, I believe, or it could be the reference manual. And it's some theorem. It's given as an exercise in the Isabel tutorial. But let's do it. Let's do it right now. And there is a meaning behind it. If you're really curious, I can explain what this is proving. But let's imagine that I gave you the following instruction, that you are going to match things that look the same. So for example, this TXY and this TXY look the same. And this AXY and that AXY look the same. So what I'm going to let you do is I'm going to let you drag a subformula. So when you're under a formula, it is underlined, right? When your mouse is hovering over a formula, it's underlined. If you're using a touch device, the underline will not be visible, but it basically picks the smallest formula containing your position of your finger. You can drag it, and then you can drop it, okay? And then when you do the drag and drop, something happens internally. I haven't told you which logic, which proof system, whatever. I haven't told you any of that, but trust me for now, and I'll tell you not to trust me in a few sentences, but for now, just trust me that this is a valid inference rule in the sense that if the premise is true, the conclusion is true, okay? If the premise is a theorem, the conclusion is a theorem. And you can keep going like that. So for instance, now I can see that this TXY and this TXY match up, right? And then now I can see, well, I can match these two guys, and then maybe I can match these two guys, and I can do something, okay? So this particular proof attempt is a failure, but you can see the interaction that's happening, right? I'm dragging a subformula and putting it on some other subformula. So I think I can explain this to maybe a fifth grader, right? Someone who's never seen any logic, any formal logic before. And it's almost language independent. You can imagine, I don't know, pictures of animals or something, and that would be just as informative as the formula itself. So this is the system. Now, this particular system, this particular proof attempt was a failure. I'll tell you how to make it succeed in a few minutes. But one thing I do want to say is that if you go back to that URL, some of you in this audience have heard my talk before, and you'll probably get bored. So therefore, what I've given you is a bunch of problems that you can try to do right now instead of listening to me if you want to challenge yourself. So there are some propositional theorems, some famous propositional theorems like the two Hilbert axioms, some classical known theorems, which is intuitionistic, and then the negations, double negations of them, which are intuitionistically true, and some first order theorems. And I would ask you to just experiment with them. So just click on any of them. That opens one of these prover windows, and then just drag and drop things and see how far you get. Okay, and I'll check back with you guys. I'll check back in a few things. Okay, so the outline of my talk is I'm going to talk about this particular approach to interactivity, and it has several levels of details. I'll start out talking about something called contextual reasoning, and then I'll show you this drag and drop mechanism, which I call proof by linking. And then I'll talk about how I deal with quantifiers, and then finally, the stuff that is new, I'll talk about hierarchical detail, so how to hide the clutter on your screen. And then if I have time, so I may not have time for these, but if I do, I'll talk a little bit about how to do tag theory, because currently that is still open, but I have some ideas. Okay, so let's talk about contextual reasoning to start with. So an observation about basically every proof system I know of is that the connectives, the primitive connectives are functors. What do I mean? I mean that if A entails B, for whatever meaning you give to entailment, that, for example, this could be an inference rule. If A entails B, then you could put A in some formula context, like you could put it in conjunction with F, and that will entail B and F. So sometimes it may be a contravariant functor. So for an implication, the direction changes, but it's still a functor always. And this is true in the first order case. This is true in the modal case for basically every modal logic and node. And this is the famous K axiom, right? So generally it happens to be true. Okay. So so this thing called the calculus of structures, it makes use of this functoriality. So whenever we have an inference, you can infer B from A, then you can put both of them in the same context C, and it'll still be a valid inference. Okay, so what is the context C? Well, in the intuitionistic case, you have to be a bit careful about whether you're on the left or the right of an implication. So the C context, think of it as conclusion-like context, or positive if you want to use the so-called polarities. So this is a positive context, so it occurs to the right of an implication. Okay, and the dual of that, which occurs to the left of an implication, is an A-like context, A-like assumption. Okay, and the notation is that these contexts have a unique occurrence of a hole, which is just this double braces. And then if you put a formula in there, that's just the result of replacing the hole by the formula. Okay, so the calculus of structures is designed to use these sorts of contextual inference rules. So here's one of Hilbert's axioms, the S combinator. Here is the calculus of structures proof of it. I don't want you to read the details. I just want to put it up there to highlight some features of it. So first of all, notice that it's linear. It's a pure real system. There's no branching. Okay. And the formula is derivable. So if this formula is a theorem, or rather, this is a proof of that theorem. If I can use these to something that is obviously true, like a conjunction of truths. Okay. But where you stop is more a matter of taste. You can stop at true, or you can stop at something that is obviously true. Okay. Completeness says that every theorem is derivable by this proof system. So every theorem can be rewritten to something that is obviously true. And there's a kind of subformula property. I'm going to skip this point because it's not very important for this particular talk. But if you're worried about the subformula relation being violated, well, there's a way you can address that. Okay, so what do the rules look like? So this is my favorite flavor of the calculus of structures. There are others. But this flavor is sequent calculus-like, because that was my first proof system, the sequent calculus. And so I like to see it in every proof system. So here we have the initial, which is kind of like the initial sequent. But I'm thinking of the implication as the sequent arrow. I'm not making a distinction between them. These are like the conjunction right rules. Okay. So in a context, if I can prove B and C, then if I send the context to B, I should still be able to prove it. Okay, something like that. Think of it as an inference rule. And these are like the left rules for conjunction. These are like the right rules for implication, the left rule for implication. So for example, the left rule for implication, like in the sequent calculus, you prove the antecedent and then you can assume the succeedent, right? Any questions on this presentation yet? So notice that these are all in a C-like context. These are all a conclusion or a positive context. All right? The disjunction rules, which should be similar to the conjunction and implication rules. I'll just skip that. So those were the rules which are sequent-like. But this system lets you do things that are a bit more general than the sequent calculus. It allows you to do composition primitively. So these composition rules work among the assumptions. Okay, so they work in an A context. And the way you think about these rules is that I have two things that are both true simultaneously, that I've assumed to be true simultaneously. What are the consequences of that assumption? Okay, when you interact with theorem proving. Always I'm thinking of it as going from the conclusion upwards, right? The opposite direction for most proof theorists. Okay, so once again, let's go back here and let's look at a few examples. Okay, so I have to tell you, okay, now this is one of the funniest keyboards I've ever used. Okay, let's look at this one. Okay, so simple proof. So here, I'm sure everybody has solved this. You drag the A to the A, right? And you've reached an obviously true fact. Okay, let's try. It's always opening a new window. That's what's the problem. Okay, let's try. Let's try the S combinator. Okay. So this combinator, if you've used any proof system, you've probably seen two different styles of proof. One is where you start from the conclusion and work backwards. So from the C, I work backwards, right? And then I have two things to prove. So I can prove the B first, right? And then this is done. And this one remains because I still have to give another copy of A because it requires two copies of A. So now this proof attempt is a failure, but I'll tell you how to fix it in a second. But before I go, let me just point out that you can use these two keys to go forward and backwards in history. Okay, or you can use Control up and down. So here the problem was that I needed 2 copies of A. So if I have my mouse over an implication, which is positive, then I can right click on it and do contract, which gets 2 copies of them. And then one of these I can send to A, the other one I can send to B. Okay, and then this A to A. All right. So contraction is something that is explicit in this proof system. This is not necessary in the design. This is just the way I've programmed it. But there is a better way of doing it, which is when you're dragging and dropping, normally you think of it as moving the formula. The source of the formula is moving to the target. But if you hold down control, it behaves like a copy. Okay, so if I hold down control while dragging and dropping, it keeps the original, but then does something with a copy of it. Okay, and so that avoids doing explicit contractions sometimes, and then you can finish the proof. All right. So that's how you do the S combinator. Now, I want to say a couple more things about it. If you've used any proof system, you've seen the backwards direction that I did here, right? So I went from the thing I needed to, so this is kind of like the apply tactic of rock, right? And then here, this will be like 2 different sub-goals. And the first sub-goal I do, well, not that, I need to go from here because I need to copy it, right? And this is the second sub-goal, and then I have one residual obligation. Okay, so that's the sort of right-hand side to left-hand side direction. But you can also go the other way, right? So you can start from things you know. So I know A. I take 1 copy of it for there. I know B, so I put it here. I know the other copy of A. And then, well, the last one, it doesn't matter which direction I go, right? So that's another option. This is sort of forward chaining or reasoning from the context. You have seen this already also in other proof systems. But here is something you've probably not seen, which is composition. So I have 2 functions. I have a function here, A plus B plus C, and I have another function A plus B. These 2 B's are in dual positions. So there is a sense in which I can compose the 2 functions by linking up the 2 B's. Okay? And I don't know of any standard proof system that allows this kind of function composition, but it is very natural in this interactive formulation. All right? So that's why I say that in the negative context, it behaves like a compositional system. Okay. So a few more things I need to say before I end the story on propositional logic. So the units are present. Okay, this is the full propositional calculus. And the way you treat the units is whenever they occur in a position where the formula can be simplified, you simplify it. So for instance, A plus top can be simplified to top. If you have top or A, that becomes top, and so on. Okay, so these are all the standard rules. Here is a contraction rule. This is explicit in my implementation. It is not necessary in this system, but it is just the way I've implemented it. And here is the cut rule. I will not talk about cut in the rest of this talk, but it is present. All right. So what are the properties of the calculus of structures? Well, if there is a derivation from A to C using those rules, those contextual rules, I mean, indeed, it is the case that A entails C. This is Soundless theorem. And moreover, if this sequence is provable, let's say in LJ or something, then there is a way to prove it. So prove A1 plus so on up to C. You prove it by rewriting it to top, okay, or true. Okay, so the question is, I've given you a proof system, but here's the thing. This proof system is not specific to any particular backend. So here, for example, if I were to export this to coq or rock, it's quite easy. So let's imagine that I have a calculus of structure derivation from A to C or from C rewritten to A. How would I see that in coq? Well, I need to fill in the green proof, insert proof here bit, right? So there are 2 basic ways you can do it. One is to take this proof system that I showed you in the previous slides and actually implement it in coq as a kind of data structure. Or you could just use a shallow embedding, which is you represent the proof steps using the very general logic of rock. So I'll show you the second thing, which is much easier. So the idea is that whenever you have one of those contextual rules, you first show that the entailment A to C itself holds, and then you just transport that entailment into the context. Okay? The 2 steps, very simple steps. So here are the transport combinators. So if I can prove A to B, then I can put it in a context and C, and I get a proof from A and C to B and C. And all of these are proved by Otto, okay? So these are all very simple proofs. And if you have a bunch of these combinators, so the AND L combinator, the INT R combinator, whatever they need, you can compose them, okay? And that will give you a transport from A plus B to some complicated context. So this context has A1, has C1 is the whole and C2. Okay, the C1 and C2 are two formulas. So that's how you transport the entailment once you've proved it into the context. And obviously the entailments themselves are also trivial. Okay, so here's one of the rules that I had on the slide, but written as an actual implication code. Again, Otto will prove it. And then when you take this implication and plug it, so this implication, you plug it in that hole, you actually get a full proof. Okay? So everyone clear how the composition is working? This is all very simple stuff, right? You could do this without knowing a whole lot of rock. So that's an example. So the K combinator, right? I would prove it by using these transport combinators, and I guess I have, doesn't really matter. I have one of them, which is the rule, and then I can repeatedly take the stuff I know. You have to read it from. So this is the premise. This is the third thing. So I start from here, and then I do a bunch of stuff, and I reach proof. Okay, so the proof is written in the opposite direction of the inference system. Okay, so that's the calculus of structures. This is not new stuff. This has been known for at least 20 years now. So what I'm going to do now is I'm going to tell you how to do that drag and drop thing using the calculus of structures. Okay, and the idea is that we're going to use this contextual nature to avoid constantly breaking up formulas and rebuilding formulas, right? I keep the context untouched and just change the things that change. Okay, so what is linking? So it takes two unrelated subformulas. Well, unrelated is not exactly correct. They must be related by some ancestral connective, and the connective must put them in opposite polarities. And it joins them up, and then there's some internal mechanism that brings the two things together and resolves that intended joins. When you drag a formula from here to there, that is internally by the system, it gets converted to something. Okay, so let's look at one specific case of the S combinator proof. The thing I showed you about dragging this B onto that B, right? So the first thing we did was we sort of identified those two endpoints, right? And then we said, so we drag the orange to the blue. And internally the system tried its best to bring the two endpoints of the link together until it met up. And hopefully it was something which could be removed. In this particular case, it did meet up in just the right place where that top could be removed. Okay, and that's why the composition that I showed you works. It's this particular rewrite. Now, one very important thing is that you don't need to actually understand the calculus of structures to follow this proof, because all you need to check is that if this is true, then this is true. Each of those lines is a small theorem that you can prove for yourself, right? You don't need to actually implement the calculus of structures to verify this proof. Okay, so a link, right? So as I said, the endpoints of the link must have an ancestral connective that puts them in opposite polarities. So in some conclusion-like context, if I have two formulas, one of which has an A, the other has a B with sort of the same parity, and if they're separated by an implication, then I can make a link between them. Okay, and likewise for assumption-like context, but here the connective is conjunction and not implication. Okay, so we start a link by this. So if I write it as an inference system, I'm dragging and dropping this. So it's kind of like starting a link, right? And then now I'm going to recast the calculus structures using this linking mechanism. It's actually not at all difficult. So let's look at a few cases. So here is the and right kind of case. So one endpoint is in this C1, and the other endpoint is on the left operand of this conjunction. and I'm trying to bring the link closer together. Okay, so it goes into a smaller context than over here. Okay, so the link just gets closer together. And so all of the rules are written so that the premise has a shorter link length than the conclusion. And the rules are basically the calculus structures rules, except I'm just using this linking technique. Okay. And sometimes you will run into a sort of ambiguity. So here is an example. So one endpoint is here, the other endpoint is here. When I want to drag them, to bring them together, there are two possible ways in which they could be brought together. Okay, so the question is, what happens if there is a critical pair? So this one happens to not be a critical pair. And most of the time, in almost all cases where there is an ambiguity, the ambiguity can be resolved by just looking at the invertibility of the connectives. So most of the cases work out. Some cases don't, though. And here's one particular example. Okay, so a little bit of a weird example. It doesn't show up a lot. But when it does, it really matters. So here there are two possible ways in which this link could be resolved, and there are two different formulas. Neither is stronger or weaker than the other. Okay, so because there is an ambiguity, we need some help from the user. Okay, the user is the only one who knows what will make it true. So the little bit of help the user is providing is the user is giving a direction to the link. Okay, so you have a source which is always orange and the target which is always blue. Okay, and so the direction of the drag determines the way in which the composition works. And the way you think about it is that the source is dragged into the target. So the source context, which is C1, goes into the target context, which is C2. That's roughly the interpretation of the direction of the link. Okay. So for instance, one of the two cases of the critical pair can be resolved by dragging this B onto the C, and the other one by dragging the C onto the B. And this resolves all the ambiguity. So there are no more critical pairs, but just this one direction to the link. Okay. And finally, when the link is of length 0, which means that the endpoints are right next to each other, then we can do some kind of primitive interaction. So for instance, if it's the same formula, we can get rid of the link and just replace it by true. If they're not the same formula, then we can just turn it back into an implication. And we can do a bunch of simplifications on the way, right? So once we have resolved the link, if the link becomes true, then as we are looking at the full picture, we can do some simplifications of the formula. So checking back on these, so let's see. So how many of you have been trying this? Did anyone try any of the interesting examples like the double negation of A or not A? So let's go through this proof. This proof is kind of interesting, right? So we know it requires at least one contraction, because in a contraction-free case, this is not provable. So let's do a contraction. Here I'm doing a copy, so I'm holding the control down. Okay. So now let's say I pick this chunk, right? So these two can match up. And then now I have the A and the A. Okay, so that's the simple proof of the double negation of A or not A. More interesting, let's do the double negation of Peirce's law. Peirce's formula, sorry. So again, this is one of those things that you can only prove with contraction. Okay, so that's one by contraction. So now I always get stuck over here. So let's see. So how it is? So this A and this A, they look the same. So let's match them up. And now let's solve the B with that. And then now we can solve the A with that. Okay. Wait, what did it? No, I dragged it the wrong place. So we drag it there. Yeah. Okay, so this is the proof of the double negation of Peirce's formula. There are lots of experts of proof systems here. Tell me if you agree or disagree that someone who has not ever used your system could prove the double negation of Peirce's formula, like within let's say a little over 30 minutes of using a system. I suspect the answer is well, depends on how clever they are and how used they are to
Out of
process
periods
this.
and log.
Hmm?
Out of periods and log.
No, I don't want to use black boxes, right? I want you to do it from, using primitive tactics, let's say. So another thing I want to say is that this system that I'm presenting, it can produce proofs in a few different dialects. So it produces COC in 2 different versions, in SWL HOL and in Lean version 3 and 4. And internally I also have HOL4, but that has some issues, so I'm not letting it out to the public yet. Okay, so going back to this, so the third level, which is about how to deal with quantifiers. So this implementation that I have works for first order intuitionistic logic. And I think it also works for higher order logic, but there are some issues which I'll talk about later. So the issue with quantifiers is that when you have quantifiers, the whole can be in the scope of a quantifier. Okay, so when you put a formula in the whole, the free variables of that formula are captured by the quantifier. Okay, so when I put A in that C, any free variables of A could be captured by C. Okay, that's the interpretation of the substitution operation. And if you think of capturing substitution, it is very difficult to formalize the meta theory of capturing substitution. And that makes it difficult to export this to various proof systems. So instead, the way I have implemented this and the way I think about it is that I think of not placing a formula, but like a formula function. Okay, a function that given these free variables or given these variables would produce an actual proposition. I guess it's like raising from logic programming. And so the intuition is that if this A has a free variable X, then I can link up that X to an actual quantified variable by that substitution. So that should retain validity. So both directions should be valid, equally valid. So how would you represent this in a system like COC? So I want to give a very quick overview of how we would do this in COC or ROC or whatever. So I'm defining a type of context which has holes of various types. Okay, so these are the types of the things that the variables are. So the definition is exactly how you would imagine a context is defined. But then what I'm defining is this type of types which have free variables of those types. And U is the type of a thing that has free variables of types TS. Okay, so it's just raising. And then there's the operation of if I have a context which has free variables of types TS and I have a raised proposition, then I can put that raised proposition by this instantiating the free variables by those variables. Okay, and these are all very standard, very easy to define fixed points. But the important thing is that you can do logic with these raised propositions. So, for instance, you can define all the connectives. So it's a definition of conjunction on the raised proposition. So these are 2 propositions that can be placed in a context which has holes of types TS. Okay, you can also do this with all the quantifiers and so on. Okay, so this whole system that I've presented has been deeply formalized in ROC, including the meta theory of it. So I actually have in ROC a proof of the soundness of the system, not the completeness, because completeness is much harder, but the soundness definitely. All right. So what do the quantifier rules look like? Well, almost all the rules are the obvious thing. So here, for instance, if I need to bring these 2 links closer together, that for all needs to go out. Right? So it's like scope exclusion. Okay. So those are the easy cases. And then there are a couple of cases which don't have a link-like behavior. So if I have in a positive context, in a conclusion-like context, I have an existential formula, then the only way to prove it, so think of this like Cantor's theorem, right? The only way to prove it is to actually supply the diagonalization argument. So I have to plug in the term. Okay, but in the for all case, when I'm done proving the body of the for all, I can get rid of the for all. Okay. And the last thing I could tell you is about how to deal with the first order predicates. So when I have 2 predicates, so this A is a predicate symbol with n arguments, which are terms. Then to resolve that link, I just show that the arguments are equal. Okay. And then you can formalize some equation theory. This is actually not that important, but anyway, it's done. Okay. And the important thing is that once you have some kind of equational theory in your system, then you can easily do rewriting. So what is rewriting? Well, if I have an equation and I have some term where it has a subterm S, then I can rewrite from S to T by just dragging the S into that S, right? And I can rewrite from T to S by dragging the T's. So I don't need to learn how to rewrite in Rock by figuring out what the context or whatever is. I could just do a drag and drop. And importantly, this is a conditional rewrite because this thing could be underneath a whole bunch of quantifiers and other stuff, right? So normally rewriting is difficult when you have conditional rewrites, but this is no problem for us. I'll actually skip this a little bit because I don't want to bore you with first order stuff, which is all very easy. Okay. So the next thing, let's go back to this and let's look at this particular example. So this time, let's actually prove it. Okay. So the way to prove it is this first formula needs to be contracted. That was the thing that was missing. It's contracted once. Okay. So now these two can match up. These two can match up. These two can match up. I can do a rewrite from X to Y. Okay. And then I can use the second copy of that formula now. And I can finally match these two up. That, okay. So that was the proof. Now this proof will require a little bit of hand-holding the first time we do it. But the operations are the same as what I've told you before. It's always dragging things onto the same thing in a different polarity. And sometimes you have to do contraction. And sometimes you have to think a little bit, okay? So the thinking is not for free. Anyway, the point I want to make is that this proof is very cluttered because you're seeing the entire proof state, in fact, the entire history of the proof on your screen at once. And, you know, this is a research prototype, so I'm not going to propose this for any actual use, but clearly already we can see this is a very large amount of information on the screen. So how can we improve the clutter? How can we reduce the clutter? So this is new stuff. What this system implements is actually something called open deduction, which is a sort of a parallelization of the calculus of structures. So the parallelization comes from the fact that we are combining the notion of formula, sequence, and proof. Okay. So now you can take two proofs and put a connective between them, and that's kind of like doing the two proofs in parallel. Okay. And you can put a proof on top of another proof as long as the premise of this proof and the conclusion of that proof match up. It's a valid instance. And there is another version of this, which comes from the fact that, so this one is kind of like these two proofs are in the same context, whereas this is kind of like they're in different contexts. So I'm taking this proof and I'm rewriting it to a different proof in a different context. I won't get into too much detail about this. I just want to show how we can use open deduction to reduce clutter. So here is that thing that we had on the screen, right? The horrible formula with a bunch of stuff in the middle, and I drag this to that, right? So once I start dragging this to that, the stuff which was irrelevant would stay outside the box, right? And the box will just focus on the important stuff that was happening with these two things that were linked, okay? And that's recursively the case. So next, as I'm simplifying this, as I bring these two together, there could be a smaller box where a bunch of other stuff gets removed. So the boxes, which are a complete nesting, they give you a hierarchy, okay? So the way we interpret this is that this entire derivation with the stuff implies in front means that if stuff implies the premise of this derivation, then stuff implies the conclusion of that derivation. Okay. Okay, so now with that, what we have is we have a mechanism for zooming in and out with levels of detail. Because if I have that box up there, I can zoom into that box, right? And then forget about everything else on the screen. And that by itself is a completely valid little proof. And I can zoom out once I'm done with that proof. So you can zoom in and out. Only one small thing to note about zooming in and out is that, so let's imagine we're trying to zoom into that box over there, right? So let's imagine that we have this full proof and we want to zoom into that small box. One issue is that the stuff in the box has free variables, which are quantified outside the box. And so once you zoom in, those free variables become the context of the box, okay? So that's one quirk of zooming in and out. When you zoom in, you don't lose all of the context, you keep just the quantification structure. And then you can zoom back in and out and so on, okay? So how does this system look now? By the way, this is not yet online, but it should be online soon. The way you do it is, the way you use this way of reducing clutter is you point to multiple things. Let's imagine you point to those two things. Okay, then you can launch the sort of subproof, you can think of it. So I put it in a box. Okay, then I can zoom into the box and just work inside the box. And then eventually another thing I could say is that once you pick the box, you may not have picked everything that you wanted up front, because you may not have realized that this F was also important. Okay, so that F ended up outside the box at first, but then you might change your mind. You might say, well, let me bring that F into the box because I need it, let's say. Okay, so I might drag the F. Remember, orange is always source. I drag the F to the target into the box. So I can bring stuff from outside the box into the box, but not the other direction always. So now the F goes in, and then as a consequence, in the bottom, that F also gets marked. Okay, so it's kind of like you mark several things in the computer that are important, draw a box around it, focus on that box. Okay, and that's your notion of level of detail. And then once you're done proving it, then you can get rid of the box and go back to the original formula. In this particular case, I didn't do anything inside this box. I just, it was the trivial proof. But you could imagine you've done a bunch of stuff inside the box, but then you can get rid of the boxes and you're back to the original formula. The original context, I mean. Okay, so in the few minutes that I have remaining, let me just talk about a few future directions. Okay. So I've shown a couple of things. I've shown linking, I've shown contraction. I haven't shown cut, but it is implemented. And there are a few other universal logical operations that are implemented. But there are some more that we could implement. One is splitting, which is if you have a proof with a whole bunch of interleaving, then you can rip them apart, so unzip the proof into two different proofs. That holds in general, but it's not implemented. And then there is a very, very interesting new direction in open direction called substitution along a path, which gives a very dramatic improvement in refactoring, which is not yet implemented, but I'm really looking forward to implementing that. I haven't told you about how I deal with lemmas yet. So, of course, I told you there is an implementation of cut, but you might want to also link with stuff that has been proved earlier, like in a theory or whatever, right? So you can imagine linking from the formula you're trying to prove to a part of some lemma that was proved earlier. So that sort of stuff would be very interesting to implement, including searching for lemmas. These are possible directions for a universal interaction mechanism. And one last thing that I haven't talked about here, but this is very active work right now, is figuring out how to deal with histories. Okay, so for us currently, history is a linear timeline, right? You always progress forward, but then when you go back and change your mind, that entire timeline is lost and you move to a different timeline, right? Because there's no branching structure in my undo operation, right? Undo is a linear history. But sometimes, and in some classical theories, it makes sense to be able to link to your own past. So linking not just in the premise of the formula, but linking to some previous formula in the lower down of the proof. And there are some interesting cases, especially with circular reasoning, where it makes sense to link between histories. So those are things that I'm thinking about right now. And do I have time for type theory? So let me just do one slide on type theory. Okay, so initially I said that this is a universal thing, but it only works for higher order logic, let's say, right? And it's still open how to do deep inference in the style of package structures, let's say, for dependent type theory. Completely open problem. And why is it open? Well, one reason could be that what does linking even look like in this case, right? So imagine you wanted to link those two things of type I. So here's a function that goes from I to B. Okay, and I have a thing of type I, so I should be able to link that, right? But what does that mean? Well, I don't know. In type theory, I have no idea what that means. But I know logic, okay? And because I know logic, I can sort of see the logic underlying type theory by some kind of realizability interpretation, where I interpret the types as formulas, okay? And under this realizability interpretation, I can think of the type that I had up there as this formula, okay? So it's kind of like Corey Howard, but not exactly. But since it's logic, and I know how to do logic with deep inference, I could try to do that kind of drag and drop operation, okay? And this works. This is a complete solution for dependent type theory. But there's one big problem, which is that this realizability interpretation, is unsound. Okay, it is complete but unsound, meaning that there are more things that are provable than are actually true in type theory. Okay, this was recently shown in 2021 by Mary Southern. X in a canonical type theory, meaning a type theory where all terms are in canonical form. So my approach right now is to figure out what it means to do this in a generalization of the syntax of type theory, where the pi, right, the dependent product is split into two parts. One, which is just a binary, it just flags a name as a name of the variable, and then a different thing, which is the assumption of the type of that variable. And the thing that is the assumption of the variable, the type of the variable, is the thing that moves around, whereas the introduction of the name stays where it is. Okay. But that's if you're curious, I can show you a proposal I have for the full thing, but I still don't have a soundness proof. I have a completeness proof, but not a soundness proof. And the reason it is difficult is that in generalized type system, I can build a derivation, but then if I want to bring out a type theory derivation from it, right? Derivation in dependent type theory, it's not easy. Okay, I'll skip this definition stuff. Okay, and since I'm almost out of time, I'll just talk about one final thing, which is about circular reasoning. So I haven't talked about induction, but induction is very important and something, let's say, very common in systems. And I personally think that the way to do induction is by circular or cyclic proofs, because with cyclic proofs, I can draw a package by just linking, right? Whereas if I have to type in the invariant, I have to use the keyboard, and I may not have a keyboard. But drawing a package is easy. But the question is, what does it mean to do circular proofs in deep inference? I think this is not completely fully resolved yet in the community. And if you're curious, this is an interesting thing in the case of linear logic. Here is a circular deep proof of something. I don't know what the meaning of it is, but it has the property that in every infinite unfolding of this cycle, the mu is principal infinitely often, right? So it satisfies some parity condition that is common in these circular proofs. So this is proof-like, right? But what does it mean? And this formula shows up in the, if you were to sort of implement full linear logic in mu-mol, this is the sort of thing that shows up in the implementation of band, okay, of the exponential. So there's a sense in which it's not completely artificial. It does actually appear, but the meaning of it is currently open. So I think I'll skip this also because I mostly talked about it. So the conclusion of my talk is that this is where I want to be. Okay, I want to be able to do proofs by waving my hands and have it generate the proof script in whichever proof system, in Mean or Coq or Isabelle or whatever. Okay, and my slides are over there if you want to if you're curious, and I guess I'll take questions.